very thank you for invitation to this to give Erwin Schrödinger's lectures. It's a real pleasure and honor for me. So I've been always working on this intersection of geometries, representation theory, and number theory. So I've been trying to use a lot of tools coming from geometry, from topology, to solve some rather concrete problem in number theory and representation theory, harmonic analysis, to calculate integrals, to compare different integrals. So today, I'll talk, I will try to, it's rather broad, so I mean, because of the nature of the lectures, I'm not going to go to something very specific, but I try to convey some general ideas how you can use topologies in particular singular spaces and maybe infinite dimensional spaces to tackle some rather concrete questions. I'm not sure how far I can go, but let's just try to begin with the very beginning. So you know, first start with a story about topology singular spaces. So for regular spaces, there is this topology of manifold that was created by Leibniz in the 20th centuries. So this is one of the main, point in this theory that you have for every manifold you can define some vector space, maybe rational vector space of rational numbers, called homology space, your finite dimensional vector space, and they have this. It doesn't look so exciting, but it actually is important tools they have of the dualities. I mean, the hi, indexed by integers, hi and hn minus I. Dual vector space, as long as F is a compact-oriented manifolds. So, all the vector space have structures. In some cases, you know that they are related to each other by some structures. In particular, this structure of duality between hi and hn minus I. It really somehow, when you start working on geometry, that you see that point duality is really the most important tool that you have to understand and control the cohomology of manifolds. And it happens that this thing breaks down completely when you look at singular spaces. So there's no longer, you can still define cohomology, but this no longer the point-correct dualities. So there have been, a lot of reflection and understand why the failures of point-correct dualities before some kind of very definitive answers. It was given in 1974 by Gretzky and Macpherson. So Gretzky was a student of Macpherson at that time, and his thesis, he defined an intersection cohomology. So another kind of homology, an IH for intersection homologies, and even for singular space, they satisfy point-correct dualities. So the failure is about the difference between the ordinal homology and intersection homologies. It happened that this have the very important thing is that the intersection homology has this local nature. So it doesn't come just as a vector space, but it's some kind of sheaf theory, something that depends locally on singularities. So it comes with the whole the full-fledged theory of sheaf, so this is a very strange name. And people still are puzzled by this name, theory of perverse sheaves. So this perverse sheaf that was invented by these people, first by Gretzky and Macpherson, and later in some kind of very beautiful form by Delin, Gaber, and Gretzky and Macpherson. So I will try to convey some idea about this theory and their applications in the. So let's first agree what singular space means, because I occasionally talk with physicists, so she don't seem to agree what singularity means. So let's try to clear at least that point. So it is an example from the singular varieties. So this curve in red of point x complex number x and y satisfies this equation x squared minus y third equal to 0. So this is a singular curve. It has only one singularity point at the cusp at 0, 0. Everywhere it is smooth curve. So it's smooth because when you look at any point, here for example, then locally, it looks like a line, right? It's just a line. Whereas this point is really not doesn't look like a line. So this is singularity points. So that is singularity mean in geometry, in mathematics in a way. It's different from, I think, the singularity of vector fields in physics. So how can you, how rigorously you can say about this point is singular and this point is not? Well, you have the Lucas functions, right? So when you have to look at the function around this point. It's just the function defined around this singular point, and you restrict them to this curve, right? So that means there's many ways to say what function defined around the point. The most naive thing is to look at on-formal series. So look at on-formal series of two variables x and y, and you agree that two formal series are the same if they restrict to the same restriction on the curve. That means the x squared minus y third is considered to be 0. So what I mean here is just we say that the formal completion of the range of function, and probably I cannot zoom here, at the cusp is this ring, right? This is a ring, a formal completion of this singular curve at the cusp. So they have two variables x and y. So this is a formal series. If any series don't drive any convergence, and divide by the equation of the curve, divide by x squared minus y third. And that is the formal completion at that point. And this is singular because this ring has no way to, it's not isomorphic to the ring of formal series one variables. So why we know that? Because these rings are local rings. That means there's only one maximum ideons. And here's maximum ideon is usually by t. And here's the maximum ideon is usually by x and y. And that is called m. And you do this operation, m mod m squared. On the left, we have number 2, and the right have number 1. So there's no way they're isomorphic. So that is, say that this is really a singular curve because although it's dimension 1, but this m over m squared at the cusp is dimension 2. So this is the field of regularities. And that if it's not isomorphic to the range of formal series of one variables. So this is what very brief reminder about singularities. So now let's come back to what I mean about the local natures of intersection complex. So this is the Goretzky-McPherson intersection homologies. So for every singular spaces, you can define this vector space, using finite dimension vector space, Hi of x. I use this upper style, I mean cohomology is homology, but it is just for convenience. And say it's local nature, that means I can consider a sheaf, ICX. A sheaf is something that they leave, somehow all around the space. In particular, at every point of the space, I have the stock of the sheaf. It's some kind of vector space or maybe a complex of vector spaces. And this stock are glued together in some way. Right? How to glue them, that requires a lot of formalism that I have no time to develop. But really, even I think the way I work every day, that I think about a sheaf, I just think about their stock. So it's kind of complex vector space of every point that move in some controlled way. So that is so when you have all this family of complex vector space, taking cohomology to what happened globally, then you get this. Then you get this. This complex vector spaces, the intersection cohomology of X. So, for example, I get some trouble with this. So one of the main points is, that the stock of, if the space is smooth, no singularities, then the IC is very simple. At every point, you just put the complex, the Q, the finite Prandtl numbers, or C. It's just the simplest thing possible. But when you have singularities, then the stock of the IC can be something complicated, just bunch of vector space connected by differentials. And the first thing we do know is that stock only depends on the formal completions. So that's what the linear C xy formal series divided by x squared minus y third. So the isomorphism class of the stock only depends on this ring. So that's something we know that is true. So somehow punctually only depend on that information, on this rather elementary and combinatorial algebras. But how they glue together depends on more elaborate information. But at least the punctual information depends only on that completion. So this is an example. Let's see how interesting this IC can be. So look at the simplest singularities in geometries you can make. This is a cone. So is y on the bottom, some smooth projective manifolds, right? And the cone is just some point, and then you just somehow draw a line to every point, right? So that gives you a cone. Well, I mean, if you want to define it somehow correct algebraic geometry, you need some kind of ample line bundle on your projective varieties, and somehow you construct the infinite section and you get to a point. That is a cone. Anyway, so the cone is not just a projective varieties, but it's given by projectivity and some ample line bundle. So that is what I want to mean. And so you can certainly look at what is the IC of this gadget, right? So everywhere, every point is smooth. Right? The variety is smooth, and of course, on this line are smooth. So the only singularity is at this point. So the only question it should be asked is what is the stock of the IC at that point? What information it encompasses? And the answer is this. So this is the primitive cohomology of these projective varieties. So we have cohomology to remove the P, the cohomology usual, and then because you have this ample line bundle, you have the Chern class. There's some structure on this, and from the Chern class, the cup product with Chern class and the cohomology, you can produce some kind of primitive pieces of the cohomology called primitive cohomology, and that exactly is what is captured on this singularity, singular point, right? So this is some of the most basic examples of the stock of IC sheaf. Okay. So now let's go more abstract. So we have this. They have one of the most important things in singular varieties, of course, this IC sheaf. But IC sheaf doesn't come alone. It comes with a whole many kind of their comrades or friends from the perverse sheaf. And these perverse sheaves form some abelian categories. So that kind of thing that you can do using algebras. It very much you can deal them as with abelian group, a module of a ring, for example. And so we can construct this elaborate object called abelian category perverse sheaf, and I see the iterative complex that I just described somehow as the object of these categories. But there's many of them, and it's important to study. And the point is that perverse sheaf, their stock, the cohomologies, give many invariants for the singularity of algebraic varieties. So you construct on this IC sheaf, the perverse sheaf, and look at their stock locally, and look at the cohomology globally, and that give you many invariants, even just a dimension, give you many invariants of singular varieties. That's a meaningful invariance. So the theory perverse sheaf is what is quite extraordinary. It has many different connections with other part of mathematics that give back and forth information and insight. So, for instance, I think from the very beginning, the perverse shift come from study from PDE. People look at the system of a partial the PDE, and PDE can be considered like the D modules, and BD the system of PDE and D modules are more or less equivalent. They're just different language. And there's some perverse shifts, some special system of PDE called harmonic PDE, and there's equivalent categories. That is very important in the 70s, and there's equivalent categories that perverse shift and harmonic D modules. And perverse shift are just solution of PDE. So that is this connection between topology and analysis. And another connection, and that makes it come full force for the perverse shift, is this connection in arithmetic. So it's very surprising. In one side, I have this. So at itself is really some topological theory that is connected to analysis through the Riemann-Hilbert correspondence and connected to arithmetic in the absolute fundamental way. It really somehow in the core of the proof of the Lean of Weierstrass conjectures, 1974. So in the Lean, when the Lean wrote up his really incredible paper, Conjecture of Weierstrass 2, he defined what's called a pure shift. So what is pure shift? So you look at X algebraic varieties over finite fields, say FQ, and he studied periodic shift. So again, periodic shift is some, for every point you have some kind of vector space over periodic numbers, or complex vector space. And he said it to be pure if for every x, every point, and for every point it means some point on algebraic varieties. Then we look at solutions of some algebraic equations in solution in some of these finite fields. And then it's said to be pure with 0 if so on the stock of this shift, you have action of some kind of Frobenius operators. In arithmetic, this is very special features on algebraic geometry over finite fields. And you want that all the eigenvalues have absolute value less than 1. And you want the same for the duon of F. And the Lean developed a whole theory of pure shift. And it's really incredible that solves, for example, the Weierstrass conjectures. But there's very few examples of pure shift when the Lean wrote his papers. And it just happened that in the same year in Massachusetts, Goretsky come up with a perverse shift. And now we understand that all main examples of pure shift are just perverse shift. It just come from this theory of perverse shift because perverse shifts are very well behaved with dualities. So it's very easy to achieve these conditions. But it's very difficult to achieve this condition because you don't know what the duality of shift is. But just perverse shift, the duon of perverse shift is perverse shift. So it just the perverse shift is made so to behave very well with the dualities, and so to in particular to give a large family of pure shifts. And so. So when we deal with perverse shift on the algebraic varieties, so those are the main tools that we have. So they are very, I think I can basically work with them as black box, I mean at the beginning at least, and they're actually powerful. That one is called the Lean theorem pure on pure shift, that push forward a pure shift is in pure shift, and the Berlingson, Bernstein, de Lean, the Kuhn theorem. So that. So let me just, because I seem to have some time, let me just add a word why why this thing is so important, and why, for example, for me, who really want to use perverse sheaf, this arithmetic perverse sheaf to tackle the question in analysis, for example. So when you do analysis, it's pretty very classical analysis. You want to calculate integrals, and you want to calculate integral depending on some parameters. You want to study how they behave and how asymptotic behavior and so on. There's a lot of other questions, and there are tools in analysis to help you to deal with that, but they are not enough. They are really not enough. If you can translate programming analysis to programming sheaf theory, then suddenly you have much more tools. In analysis, you can do basically two things. You can pull back functions, and you can push forward measures. That's just basically two operations you can do. But so the two operations. If you have some way to bring that into sheaf theory, and sheaf have 6 operations, more than 6 operations. It looks kind of obtuse, F lower star, but they are more operations than functions, they're measures. So measure you can put back, push forward. But in sheaf you have duality of sheaf, and there are just 2 more operations. And moreover, you have this really something quite amazing, the composition theorem. Yeah, so I just try to explain why it's amazing. So there's one instance some way, 20 years back, when I really realized how powerful it is, when there's some conjectures made by Kazhdan, Grinberg and Kazhdan, but some integral vanish, some periodic integral vanish, and the combinatorial is very complicated. It's actually complicated. It can be proven, maybe it's not a new reason, it can be proven by representation theory, some other way, but geometrically, why you have the integral vanish? And it happened that it's actually an easy consequence of the composition theorem, because this integral alone is complicated, but it is direct factors. At the sheaf, it direct factor was something else. But you can prove something else, the whole thing is 0. Right? By the situation, you can the sum of like 10 functions are 0. But because if as sheaf, they are not functions, they are sheaf, they are vector space, the direct sum is 0. So each of them has to be 0. Right? So that argument you can do with sheaf, cannot do with functions. So just because the way you translate from function to sheaf give you this more decomposition direct factors. And if you have the sum to be 0, on the sum has to be 0. So that is one of the most elementary example on how to see why this how we move from function to topology that have to deal with some very concrete questions. Okay. So let me just summarize some main. So this application of a perverse sheaf integration complex has been very spectacular, particular to representation theory. So this is some of them. So this is, I think the first was this Kazhdan-Lustig conjectures. So in representation theory, there is this very natural, this very fundamental question of how to decompose Wegman modules. You induce some representations, and how to decompose to irreducible representation. What are the component series? And Kazhdan-Lustig come up with some conjectures to give them this on the invariant coming from some stock or some perverse sheaves. And that was the first some kind of spectacular, come up with a conjecture first of how topology can explain some algebraic phenomena. And this, it was proven in space of a couple of years by Kashiwa and Wilinski and Bellinson, Bergstein, and so on. So this was one of the first spectacular applications. And then, of course, there's this theory of character sheaves of Lustig. So, even for finite group, that representation are characterized by the characters. A group is finite, there's finite many characters. But how do you construct concrete characters? It's very difficult. But at least for the group of Lie type, that means they're like a GLN of FQ, so like a group of matrices, we call it finite fin or S or FQ, they are a theory. That was due to George. Lustig played a very big role in this story. So instead of, he can construct a perverse sheaf on the group, so that when you take the trait of forbidness, you get the characters, almost characters, it's close to characters. And he can basically construct on the character of Lie group finite type using the theory of perverse sheaves, equivalent of perverse sheaves. So this is one of the other spectacular application of perverse sheaf into theory of representations. And on the Springer correspondence, he relates the unipotent or nimpotent conjugacy class in the group with a representation of the Weyl group. Right? In the case of G and Len, you have this nimpotent class, and unipotent class are classified by partitioned. How you write n as sum of integers, right? So representation of Weyl group of the symmetric groups. So they are in some kind of bijection, at least combinatorially. But that bijection can be generalized to all group in some more conceptual way. It's not just observation, but that conspicuous correspondence. And so recently it get more elaborate. So there is this so-called geometric Langlands programs. So this is no longer a representation, but some automorphic forms. So there is at least a part of it is about to construct called automorphic sheaf. So construct automorphic sheaf. So well, it can be realized in some case for GLN mainly by Denis Gesgoy, for example. So this also from perverse sheaves. Automorphic form essentially also perverse sheaf not on the group, but some complicated stack of vector bundles and so on and so forth. And also my contribution is using theory perverse is proven fundamental lemma. So I'm not going to place it today because in the statement it takes some time to explain statement, but it is at the end of the day, if it's just one integon equal to another integons. They are very complicated integons, and there's no, the first side, there's no easy way to see how they are related, but they end up to be equals. And I use theory of perverse sheaf to prove it, to construct some perverse sheaf, and I prove they are isomorphic. And the perverse sheaf, the very notion, the concept of the perverse sheaf is instrumental to formulation of the proof. And of course, we come up with all the theory of topology of singular space, of integrable system, and so on. But it's not what I want to talk today. Okay, so now let me move closer to topic of my talk. So in groups, in representation theory, and also you're really interested in so-called loop groups. So this is example loop group. So let G reductive group. So let's say let G to be a G and Len, pair matrices, and they have loop groups of G. Is a group of matrices, but with coefficient in low-rank form series. So these are the loops. And the positive loop groups is those with matrices with coefficient in formal series, so no poles. So the difference between this is a straight L, and this is some kind of curly L for loop, and for you can arc space, arc of groups. So we really, understand the representation of these loop groups. And they are connected to others. For example, if you replace a complex number by finite fins, then you have a similar object, that group, the matrix with coefficient in formal series in FQ. So those are also called, they become more arithmetic. Those called the low confine of characteristic P. And of course, this is very similar to that it's completely arithmetic. You replace a formal series by ZP and Laurent series by QP, the periodic numbers. Right? So instead of loop groups, of group with the matrices with coefficient in series complex numbers, you can just look at it's very similar to matrix with coefficient in periodic numbers, for example. And so that, of course, is very important in Langland's program. It's low and complex Langland's program. So you really want to study this object in kind of parallel way. And one of the main, it's not an idea, it's about a dream. So Kazhdan had this dream for many years back, and he really wanted to construct a character sheaf on loop groups, very similar to Lustig on groups. So we want to construct the character sheaf on loop groups. You see and here the big difficulty is the following things. You really want to see the L and G as a group of infinite dimensionals, right? Like this. You see, a formal series is x0 plus x1t plus x2t squared, and on this x0, x1, x2 are to be seen as variables, right? From one formal series, you have infinite many variables. And now it's like n by n matrices. You have n to the n squared formal series, and so we have n squared times infinite many variables. And they satisfy equations, and I have to write on them down. So usually what you get is infinite many variables with infinite many equations. And so it's just not finite dimensional. So it doesn't. The main thing when you move from finite dimension to the infinite dimensional, usually you lose dualities. You lose very bad dualities. And if the Perverse sheaf is the very definition, it depends on duality theory. And so we struggle to understand what Perverse sheaf are on those arc space, loop groups. But because we know that the representation theory on this group are relatively well behaved. We have conjectures. We know a lot of things about this, and we really believe the Perverse sheaf on loop group does exist. It might be something rather beautiful. But we still struggle to define to build something very basic. What are Perverse sheaf on the arc space and loop space? So that's what I am to try to. We haven't not completed yet, but we do some first step to it. So let me explain what is arc space algebraic varieties. What did I just say? So let X be algebraic variety of finite type over K. So that means that I have finitely many variables, x1, x2, xn, and finitely many equations, P1, P2, Pm, which are polynomials in those variables, right? And so, for example, the K point of X, I chose the set of solutions that x1, x2, xn in K to the n vector space, so that when apply those polynomials to the point, you get 0. So this is the set, the point, and this is some kind of definition of the ring. Right? The ring is two functions on X, two polynomials from the other are the same if they differ by a linear combination of those polynomials. So now when you have this X, this algebraic varieties of finite type, finitely many variables, finitely many equations, you can do the arc space. So today I'm not talking about loop space, I'm talking about arc space. So arc space just, we decide that the K point of Lx are the K double bracket T point of X. So what does it mean? Just x1, xn, which are not in K, but are the whole formal series, K bucket T to the n. And you still require this condition. This, if you apply PI to those things, you get 0 as formal series. So that means when you apply PI to x1, x2, xn, when you add formal series, you get formal series. When you multiply formal series, you get another formal series. So when you do this, you get a gigantic formal series. Right? You just instantiate x1, xn by formal series, then you get some gigantic formal series. And you want that formal series 0. All the coefficients have to be 0. So if you start with n variables and m equations, you end up with infinite many variables and infinite many equations, right? So then that is the basic struggles. So this is Lx is defined by infinite many variables and infinite many equations. So intuitively, you want to understand arc space as a space of maps, right? So the formal series can be thought about as a disk, right? A function of a disk. And so the point with value in formal series can be thought of as map from a disk to your space. So that I try to draw those arcs. So this is an arc, this is another arc. So those are, and you have, this is your varieties, and you have many of those arcs, right? So another way to think about arc space, this is more algebraic, is to think about the limit of the jet space. The jet space is this. So the n jet space is the x, but with value in kt to the t n plus 1. Right? So you do the same, but instead of whole formal series, you just look at the truncated formal series to the order n plus 1. Right? And then you set the same equation. So for instance, if you look at the first jet space, so just instead of x1, you look at x1 plus x1 prime t, right? And no t squared. And put the same equation, and you actually look at you get the tangent vectors. So this J1 of x is the tangent bundles of x. And J2 is just more derivative and so on. And of course, the arc space the whole jets. So this thing is actually quite very simple. I mean, so to speak, in the case when x is a manifold, it's smooth, then on those are basically vector bundles. So Jn plus 1 is smooth. It's basically a vector space, a fiber vector space dimension d, I guess. And they're surjective. So smooth and surjective. It's just x and a tangent bundle, which is smooth over x, and something that is like a bundle over tangent, and you can keep going. So just view vector space over vector space. It's nothing, from a singularity theory, nothing happens. But when the x is singular, it's on, the whole thing goes wrong. So this map is neither smooth nor surjective. So you cannot rely on the jet space to provide some kind of finite dimension model for singularities of arc space. So that is something you need to, well, when you start the arc space, you need to put on the head at the very start. So we define the arc space as the limit of this jet space, but those jet space do not have they do not capture singularities of arc space. So the first intuition that you can come up with 50 years back is, the many things that you can, singularity of x can be captured from topology of arc space. So in particular, this called Nash conjectures. I'm not going to mention what it is, but it's one of the things that people, many, when x is a rational singularity, then arc space has some kind of properties. So there's a kind of basic studies when the main slogan is like you can singularity and x can be translated in topology of arc space, because you can and look at arc space like you just look at the point close in loop, the loop space with a loop, right? And you look at many loops possible, and the topology of that vision give you some information about singularities, and so that is I mean, this is developed theories. But I'm not really interested in this. This is an interesting question, but I'm interested in other questions. I'm interested in the singularity aspect itself, because I want to study function and do integration, all kind of stuff on R space and then R space. Okay, so that's what I'm interested in the singularity of R space. So first of all, you cannot usually have to discard two bad points, so the non-degenerate point. So first of all, you look at you can decompose X in a smooth part, X smooth, and a singular part, right? And so a point in R space is a map from the disk to X, and I only look at the non-degenerate arc, that map, the puncture disk to the smooth part. So you can allow the 0 point of disk go to the singular part of the varieties, but the whole disk, I don't want the whole disk to go inside the singular singular strata. So that is called non-degenerate arc. So let me look at the pictures here. Maybe have a picture. Yeah. So let's think that this thing is like a singular part of the varieties. I only want that the arc that allow to intersect with the singular stratum, but it's not entirely inside. So they're called non-degenerate arc. And I really want, I mean, we are not there yet, but we understand what, for example, the perverse sheaf on the space of non-degenerate arc. So the first, I mean, for now, the best information we have on this is very well behaved if you do formal completions. So, right, if you, so when you have the arc space, you have this gigantic ring with infinite many variables, you have infinite many equations. It's really nasty rings. But if you can look at the completion at the point, you divide by the maximum ideal and the power 2, power 3, power, it becomes a formal completion. And it makes it very simple. After conformal completion, it is basically finite type. That means you can, after a clever change of variables, instead of infinite many variables, infinite many equations, you can get just finitely many equations. So infinite many variables, but only finitely many equations. So that can be said as the following way: there exists some algebraic finite type, so Y, where there is finitely many variables and finite equations, and a point Y on that. So that the formal completion is isomorphic to that formal completion times the infinite power of the disk. So that means that you have this ring which captures all singularities. But it can be defined with finitely many variables and finitely many equations. And after that, you just add 3 variables. There's no more equations. So all the singularities is in this. I mean, from formal series is in this ring, which is of a finite dimension, of a finite type. So at least we can, so then you can, and then you don't know what is an intersection complex on the arc space, but at least you can imagine what is the stock, right? Because you know that I say that over algebra variety of finite type, the stock of the IC only depend on the formal completion of the point, right? So I just do this. I start with a non-degenerate arc. I use this Grinberg Kazhdan theorem to write this completion as the product of something of finite time infinite many disk. And I took the IC of the intersection complex of Y and look at its stock on Y. And I declare that the stock of the IC at X is the stock of the IC at Y. I can do that if I can prove that is independent of choice. If I make another model, finite time models, I end up with the same stock. And that actually I can prove that. So although I don't have the intersection complex on the arc space, I can define what are the stock by this theorem and prove some kind of equivalent calculation. So that is what I did in a paper with a joint paper with Boutier and Singularities. And so when the fin is finite fin, I can get the functions. Right? For every point, so here is Y is algebraic varieties, and then you can get the IC function to check the trace of forbiddness on the stock of the IC shift. They give, instead of complex, you get a number. That's easy to do analysis with numbers. And then I can do the same thing for the arc space. I can just look at what is the model and to define the IC number is IC number at Y. And of course, I have to prove that this is independent of the choice. But this can be proven. It's actually not very hard. It can be proven. And so we have a canonical function on the non-degenerate arc. And that function, at least you don't have perverse, but you have a function that gives you some invariant singularities. And you can compute some examples, some very nice examples. For example, for Toric varieties. So for this, the simplest singular space, you can do is Toric varieties. So let me contradict what Toric varieties is. So Toric varieties, it has a torus T, so like a multiplicative group to the power n, some n. And so I still have 10 minutes, right? Yeah. And so Toric variety is some varieties that contain T as open subset and T act on M. And here I just look at the simplest one with normal of phi embedding. So normal of phi varieties can torus varieties. And that can be very easy classified by combinatorics. So the torus have this, it controlled by this group of co-characters. So home office are from multiplicative GM to T. And the Toric varieties is given by some cone strictly convex rational cone, sigma m. Basically, those homomorphisms from GM to T that can be extended into a map from the alpha line to a Toric variety. So it gives some cone. And you want the condition, you have to be strictly convex cone. There's no line inside that cone. And so you can describe somehow the non-degenerate arc using this cone. So it's basically the cone up to the action of the torus are given by the integral point of the cone, lambda. Right? So when you look at this function, you just do some kind of experiments. When you define this IC function on the arc space of Toric varieties, right? And then define a function on this. And basically it doesn't change because the torus doesn't change singularities. So you just ask yourself, what is the number that can be attached to a lambda, some point in the cone. So this is the lattice, and well, we can. This is a strictly convex cone. Right? So now you want to say that if you have a point in this, what numbers can be given to this number? What's the singularity number of this point? And the answer is kind of obvious to think about it. It has to be the partition function. That means when you have a cone, so a convex cone, and have this race, right? This race, and the race has some kind of primitive vectors on this race. And for every element inside the cone, you can say, well, how many ways you can write these numbers as a positive integral combination of those primitive vectors. And this happens to be the IC functions. This is the result of this. So these partition functions. So this is very much like a toy things. But the reason is what's important for it is this very similar things, but you replace the group, the torus, by reductive groups. So like Gn and so on. And it happened that, and it's not, I think I'm surprised it's not very well known, Toric varieties, everyone knows what it is. But when you replace the torus by a reductive group, after all, it's a natural question to be asked, what replace Toric varieties when you replace the torus by a reductive group? And they actually have a rather well-developed theory, but this is very unknown, called the reductive monoid. Right? So when you have some non-mono of 5 varieties containing reductive group, so that the action of G on its cell by left and in the right translation can be extended to this non-mono of 5 embedding, then it has to be a monoid. So the multiplicative structure has to be to extend. So that is this theory of monoid. And it just happened that it have, so the monoid is something that contains G, has open subset, and you can multiply. It's like the matrix contains the invertible matrices. But you cannot inverse anymore. So in the boundary, there's no inverse. So you can look at this. So what the non-degenerate arc, so those arcs map from the disk to M, so that they map the puncture disk to G, right? You allow the point 0 of this go to the boundary, but you don't want that the whole disk go to the boundary. And so you can define the IC function on this. So just number. For every point in this, you have these numbers. And the answer is kind of combinatorial and very interesting. And I cannot write it down. It's very complicated partition functions. But they have very significant answer by Langlands dualities. That means this is connected to L function. You know, the whole theory of automorphic forms is based on this thing of L functions. And what you can prove is these beautiful identities. So this paper with Boutier, my former student, and circularities, myself. So in the case of periodic group or group of finite fins of a form of physics, the trace of this IC function on any representations is given by the L function, basically. If the representation is unramified. And if it is not unramified, then it's just 0. You just pick out an unramified representation and then assign the L value for that. So this is absolutely fundamental object in Langlands theory. And the combinatorial is extremely complicated. And if you know what it is, you basically have to, so you have something called the dual group. And you have to look at the character of rho plus sim square of rho plus sim third of rho, etc. So rho is any representation, and it takes sim square. So it from the combinatorial point of view, it's absolutely atrocious. So you can do this sim of sim many times, and take the direct sum over on n. So it's really not understood from the combinatorial point of view. But it happened just this function that you can define as IC shift on this arc space. Okay. So we are very happy about this, and then we believe that the perverse shift on arcs, it does have some important significance, although we haven't defined yet what the IC is, because you just know what the formal completion are. You don't know what the rings are. So now, the question how to define intersection complex, and more generally, perverse shift on those arc space, because we didn't know that they encode some very complicated, very meaningful function for harmonic analysis that cannot be treated by combinatorics. This thing is just, I think it's the typical thing that go over what combinatorics can deal with, when sim of sim. But it can be encoded by topology. So first, it's not enough to understand formal completion of point. We know that is what we know by Grinberg Kazhdan. But you need to understand what the, formal completion of point is the following thing. You look at the, look at the, this C and the CT mod T squared. So it's just very slight thickening, and CT, so spec of this to T soft. So it's just some kind of union. You do thickening and just thicken more and more. So the union among this is somehow this thing. So you actually start with some odd thickening, and we do some kind of union. Whereas in sheaf theory, we have to look at neighborhood and do intersections, and to do in the other ways around. So it's not enough to, I think it's not enough to do this. We need to understand what are the neighborhood, the right neighborhood in R space. So I think Erwin has some idea about this, but still we are not kind of stuck now. We don't understand yet what is the right topology on R spaces, and so that you can construct a sheaf theory. And for example, how to generalize this Grinberg, Drinfeld, Kazhdan on beyond the formal completions. And so what in a recent paper, I did something that is probably not very smart. I really just look at how Drinfeld proved the Grinberg-Kazhdan theorem for formal completion, and try to generalize it where I can generalize it in kind of by brute force. So what Drinfeld do is he use on two tools, the Weierstrass preparation theorem that we will know, and the Newton method to approximate solution. Right? Okay, there's a Newton method that, well, maybe, I don't know, you check a point, right? If it's not a solution, you draw the tangent, you get this one, and so on. You get closer to the 0 point. That's called Newton method. You use successive derivative. And what Drinfeld do, he put that on this can be generalized from when the ring, the test ring, from the fin to Artinian rings, to this kind of ring. It's just generalized. And he used that to prove this beautifully, the theorem of Grinberg-Kazhdan. And I just try to how to go from Artinian ring to this kind of ring to arbitrary ring, because when you do morph, you have to arbitrary rings. Of course, it fails badly, but I want to study what the nature of the failures of it. So that come up with, I think that gives some ideas about what type of neighborhood we have to consider. Something you could call Weierstrass time morphism. So it looks like very much like the Weierstrass preparation theorem. It looks like a smooth map for infinite dimensional varieties, but which are not smooth in arbitrary, in usual sense. And also it can uncover some very bizarre problem when you look at arc space. So when you look at the rings of function on arc space, so this infinite many variables, infinite many equations, you encounter a phenomenon you don't see in usual algebraic geometries. You have a lot of elements which vanish at every point at infinite many orders. So it's not just important, but infinite many unimportant. That's very bizarre. So usually, how can it be possible? A function that vanish everywhere at infinite many orders. But there's a lot of those functions on R space. So that is kind of thing that goes again Newton method, for example. So these studies of this kind of maybe simple-minded attempt to generalize Drinfeld proof give you some ideas about how to construct neighborhood in R spaces. So anyway, so if you with this type of neighborhood, when you have to kill these infinite radicals, and you take as granted that Weierstrass morphisms are neighborhood and so on, and then you can reduce. You can actually reduce R space into something finite dimensional, although not a finite type. So that is what you can reduce to. What I call the scheme of strain type. So this is what you can reduce to something like this. So this is one typical example of scheme of strange type. So this is of a plane x and y, from which you remove the y-axis, and then you add in a 0 point. Right? So this bizarre thing that when you learn the first quadrant geometry, this is not a scheme. This is a constructible subset. It's not a scheme. But actually, it is a scheme. It is a scheme. You can write down a range of coordinates so that the spectrum is these funny things. It is not a finite type. Infinite many variable infinite equations. So just you start with a finite, you blow up 0 point, you remove something, and you blow up again, and the positive limit of those blobs give you this funny gadget. And somehow this is what does the best somehow, as far as I believe that you can reduce arc space to this kind of gadget. So it's kind of a finite dimension scheme, but not a finite type. And then somehow the next step would be to study some kind of duality theory, analytic duality on those strange schemes. And that would probably hopefully give us some answer to some perverse on the arc space, because those are the modons of arc spaces. So just look at this very bizarre thing that at those points, it looks like two-dimensionals. But at this point, the only line that allows to pass is a horizontal line. There's no vertical line, no diagonal line, just one line. And so this point is one-dimensional. If you complete the rings at this point, it's the same as completion of the line at this point. No difference. It's just k to double bracket t. But at this point, they have two variables. It's one variables. So that is very typical in arc spaces. And that's it. Thank you very much.